free to start.
Okay, well, good afternoon, everyone. This is Bennett Brooks with the Consensus Building Institute. Thank everyone for joining. I suspect a few more people will join us as we roll forward here. But on behalf of Philip Orton and Sarah Fernald and Kristen Marcel, who's not with us today, and Ziyu Chen, thank you all for joining. Philip has been leading a very interesting year-long study looking at the potential effects of surge barriers, and we've been working with a pretty large group of agencies and researcher scientists and NGOs, local, some national, some from abroad as well. Over the course of a year, we've had a number of meetings, and this is a chance at the end of this study to step back and share some of the key pieces. I'm going to hand it off to Philip here in a second, but just to review for all of us the protocols that we'll be using today on the conversation, just kind of what we expect from each other here, just so we have a good conversation over the next hour. Most importantly, be comfortable. You know, we all stare at screens too much, but also be focused. There's a lot to cover, so staying focused on this conversation will be helpful. We'll have about a 40-minute presentation, but we definitely want to have a chance to have some questions from you all. There'll be a couple of ways to do that. In the Q&A box, you can post a question, or you can just raise a virtual hand, and when we're opening up for comments, I'll invite folks in. For those of you who do choose to come in by voice, really ask you to be very mindful of leaving time for others. We won't have a ton of time for conversation, so keeping your comments and questions short and giving Philip a chance to reply and others to fold in will be appreciated. And of course, stay on topic. You will all be on mute throughout the webinar unless you're looking to come in, and then I will take you off. Philip, if you'll go to the next slide. Okay, and just to reiterate the two different ways you can come into the conversation. If you look at your Zoom panel, either at the bottom, if you put your cursor towards the bottom of the panel, or towards the top, depending on what kind of computer you have, you should get a bar that looks something like what you're seeing here. It's the audio settings, and then there's chat, raise hand, Q&A. We're not going to be using the chat today, but if you do want to get into the queue, again, to ask a question, you can just click on the raise hand, and that will signal to me that you want to get in, or you can put a question in the Q&A, and we'll work through that too. And again, we'll try to get to as many questions and comments as possible as time allows in the hour. So I think that's it. Philip, over to you.
Super, thank you, Bennett.
Yep.
All right, thanks for attending today. Let me just hide my floating meeting controls. So the presentation title is Assessing the Physical Effects of Storm Surge Barriers on the Harbor and Hudson River Estuary. Work largely done by Ziyu Chen, PhD student, with myself supervising and part of a dissertation. And thanks also to Bennett and other collaborators, Sarah Fernald and Kristen Marcel. There is a web page on my own web page, easy to remember that part of it. I won't give you the whole URL, but it's linked under the different projects on my webpage. If you want to download reports, such as from the science workshop or other workshops that we had. And the funding's from NOAA's National Estuarine Research Reserve Science Collaborative, and also from New York State Energy Research and Development Authority, NYSERDA, and some work I'll review briefly from 2018 was funded by the Harbor Estuary Program. All right, so brief outline. First, I'll give a little background on the Harbor and Tributaries study of storm surge barriers and other solutions for risk reduction from flooding for the region. And I'll speak about the research, the bulk of the talk on the research on estuary physical effects, starting with a brief review on the effects of open surge barriers on the estuary physical conditions, that work from 2018. Then the recent work, basically two publications are planned. The first one's already submitted, the evolution of closure frequency and duration with sea level rise. As sea level rises, can be more need for closing the barriers because of increasing flood frequency. And then secondarily, the topic is influence of closed surge barriers on estuary physical conditions. And then we'll outline some of the future work and the conclusions of the research, and have time, 15, hopefully even 20 minutes for Q&A. All right, to review the New York, New Jersey Harbor and Tributaries Focus Area Feasibility Study by the Corps of Engineers partnering with New York State, New York City, and New Jersey. Just a brief a bit of information history. The objective is to generally to manage risk of coastal storm damage in the study area. It started in September 2017, or actually a milestone in 2017 was identification of preliminary alternatives, which I'll review. They released an interim report in February 2019, and then working all the way up until this winter, they were planning on releasing a draft feasibility report this summer, but they haven't been funded for this fiscal year, so the project is stopped, and definitely it's on hiatus. The alternatives they were looking at were alternative 1, no action, all the way up to, and then various alternatives including surge barriers and varying amounts of in-water measures, meaning surge barriers across the harbor with gates, all the way across to alternative 5, more toward shoreline-based measures along the perimeter of the estuary. So it's not just about a surge barrier study. But alternative number 2, shown with the purple line, which has a barrier often called Gateway, off between Sandy Hook and Rockaway, and then also a Throgs Neck barrier on East River. And then we'll also briefly, some of the work I'll show today actually is, more of the work is about alternative 3A, which is the light blue colors. It involves primary barriers at Verrazano Narrows, and then there's also one at Arthur Kill and the one at Throgs Neck. And I won't speak about any of the other barrier alternatives. So alternative 2 and 3A are ones that we've studied with our modeling. All right, and then the Corps of Engineers has been pushed increasingly to incorporate sea level rise or to protect against sea level rise. I think that wasn't initially in their mandate, but there was recently a law passed in New York State, I believe, or I've heard about a law that would require them to protect against sea level rise or evaluate that. And so that's always been a big issue, but they've always had it in their study as one of the factors they're looking at. But the storm surge barriers are more for protecting against storm surges than sea level rise. And I'll show you why that is in today's presentation. And so the different scenarios of sea level rise that are being accounted for in their study, that they're mainly focused for their benefit cost analysis and analyses of damages on the trajectory intermediate that the Corps has, which is shown in the light blue or even teal color. That's about 2 feet by the end of the century. The high Corps of Engineers and the low Corps of Engineers are also shown here with most of these dots, but then they're also going to look at, I think, the New York City Panel on Climate Change, sort of a high-end 90th percentile sea level rise scenario as sort of an uncertainty analysis or a sensitivity analysis, and that's about 6.25 feet by 2100. So they're also looking at that, but their benefits and costs were going to be computed using the Corps intermediate sea level rise scenario. And one other important piece of review of the HAT study is, well, just showing one of the more widely known barriers that's been proposed is the Verrazano Narrows barrier. And the components of these barriers, this is pretty typical, what's shown here, include a large, in this case, a very large navigation gate area, a smaller navigation gate area, and then off to the west or on the left, this is a view looking north, off to the west on the left is a lot of auxiliary flow gates. So I don't know if that'll come up today or not, but there's these auxiliary flow gates that are easier to open, and then there's these larger navigation gates. But this is a typical example of how the surge barrier, the different components. All right, so first I'm going to, in terms of the research, review what was done in 2018, just with 2 slides. In 2018, Harbor Estuary Program funded us to study, using existing models, we had what was called a preliminary study of open surge barriers and how, with varying amounts of openness, gated area that would be open, what's the varying effect on the estuary. And so both preliminary, and there is a report from Harbor Estuary Program and Hudson River Foundation support that you can get on their website, or I believe it's on my website, but if it's not, I'll need to post it there. Orton and Ralston, 2018. And in that report are these conclusions. Both preliminary modeling and academic literature provided consistent qualitative conclusions more restrictive barriers lead to stronger tide currents and mixing near the barrier gate openings. Widespread reductions in tide range, currents, and mixing through the rest of the estuary. Increased stratification in the estuary due to the reduction in tidally driven mixing, and greater salinity intrusion due to this stronger stratification and estuary circulation from the reduction in tidally driven mixing. And more pronounced changes on spring tides than neap tides. Actually, the changes on neap tides were very subtle, and it was the spring tides that were steered more toward being weaker currents and weaker mixing, a little bit more toward being like neap tides. Now, just some adaptation of these conclusions that I just made in preparing this presentation, sort of a 2020 update of what we know. Surge barriers proposed in the harbor and tributary study have a 55 to 60% open gated flow area. So they actually have a lot of openness to flow to the tides. So they're not extremely constrictive based on those results in that prior study. The reductions in tide range would be about 3 to 6%, depending on which barrier systems are used. For example, if it's the Verrazano Narrows, Alt 3A, the Verrazano Narrows, and Throgsneck, it's about 3% based on the modeling that we did. But if it's Gateway, it might, I think it can be a higher percentage. It's shallower waters out there and it has a slightly different impact. So depending on where these barriers are, you can have different effects. And then also reductions in currents and mixing through the rest of the estuary. You have increased estuary stratification due to the reduction in the tidal-driven currents and mixing. And with the ROM simulations done by Dave Ralston in that preliminary study, that showed a 40% reduction in stratification or increase in stratification on spring tides. Again, that was with the Gateway, the barrier system furthest offshore. But any other, I don't know what the Corps of Engineers results give exactly. So basically I've said up to 40% on spring tide with that system. And with our own model from Stevens, we had about 30% reduction or increase in stratification on spring tide. So there is a moderate increase in stratification, and then a small increase in salinity intrusion, which occurs after spring tide or on or after spring tide due to the stronger stratification and estuarine circulation that occurs because of that weaker mixing and weaker tides. All right, so the first paper that's been submitted from this research, I'll go through here in about 10 to 12 slides. It's submitted to the Journal of Marine Science and Engineering. It's available by request. If you send me an email, I'll let you know how to get it. But it should be out of review and published within a few months, so it shouldn't be long if you want to wait for a final version of that. And again, lead author is Ziyu Chen, PhD student at Stevens. Thomas Wall from University of South Florida is also a co-author. Title: Surge Barrier Protection in an Era of Accelerating Sea Level Rise, Quantifying Closure Frequency, Duration, and Trapped River Flooding. So we look at how those would evolve with sea level rise, and we discuss the different management approaches that could be used. So an important term here is the trigger water level for closure. So basically when there's going to be a flood, there's something decided as being that water elevation that's a trigger. It could be moderate flood or major flood. Those are defined by National Weather Service as various water levels, increasing water levels. Those are shown on the right here in a probability distribution. And with the past or the present day in red water levels, those are very, very rare that you have water levels of that magnitude. I think moderate flood around Manhattan is only exceeded about once per year right now. So it's fairly rare that we have flood levels at Manhattan. Now, the closure frequency and duration, however, with sea level rise, the frequency, both of these can increase. So the frequency, as you can see here with the dashed distribution of water levels, the blue dashed line, with a moderate amount of sea level rise, you can drive the system to where, and this is much like heat, global warming and heat waves, you can drive it to where you have much higher frequency of exceeding some threshold. So the moderate flood threshold, for example. And that's the sea level rise of RCP 4.5. I'll talk briefly more about that. Central estimate, sort of a central estimate of sea level rise toward the end of the century. And then also the duration is defined in this study as being the number of successive tide cycles with some time where there's an exceedance of that trigger water level. So it doesn't have to remain above it through the whole tide cycle, just have to exceed it during the tidal cycle. So here's a case of a closure duration considered to be 3 tidal cycles, so about a day and a half. But sea level rise, as you can see here, raises up the water level for all those tide cycles. And so in the case of sea level rise, you have a longer duration of closure. So it's 8 consecutive tide cycles. And we're assuming here in this research that you don't open and close the barrier when you have low tide. You don't open it up again. And this is definitely appropriate. It's more appropriate for the larger surge barriers and the navigation barriers that I mentioned. So that's the definition of duration of closure and a sort of simple demo of how frequency and duration both can increase with sea level rise. And then the last topic, which I won't talk about in detail today, but I'll show the conclusion, and it's also in the paper, is that this increase in frequency of closure and duration of closure leads to more trapped water in the estuary. So the longer duration closures can, for any one storm, if you have a higher sea level, you can have a longer duration of closure, and that you start with a higher water level due to sea level rise, and also you trap more river water if the barrier is closed for 8 tide cycles instead of 3. So I'll also give the conclusion on that part of our research at the end of this section of the presentation. So here's a diagram summarizing the methods. First, we start with observed water level data. We don't use a theoretical probability distribution or anything like that. We just use the historical data from the past century of water levels at Manhattan. You could do the same thing for Jamaica Bay or any waterway in the area, but we're going to be focusing on the Battery water level data as a simplification. Then there's also we'll incorporate the impacts of forecast uncertainty, and we'll add on sea level rise, literally add it on. We're not modeling for this frequency and duration part of the study. We'll superimpose the sea level rise. We're going to use a constant 2.3 meter or 7-foot NEBD 88 trigger water level. That's what the Corps of Engineers is using. It's a little bit below major flood level for New York Harbor. And I'll get to these other parts in a moment. But the main things I'll focus on are the gate closure frequency and duration analysis. And also I'll talk about the forecast uncertainty, the importance of forecast uncertainty in leading to more frequency, a higher frequency of closures. All right, so the data processing of observed water level, we start with the observations from the past century. We remove a trend in sea level. It doesn't have to be a perfect model. We're just trying to get rid of that trend. So we have a data set on the bottom right that represents the variability of storm tides, of water levels without the sea level rise influence. So this sort of represents the storm tide or the flood hazard. So we compute the semidiurnal maxima. That's what are shown on the bottom right. They're the half daily maxima over that whole period. And that represents the stochastic or random storm-driven and tide-driven variability in water levels. All right, so the impact of forecast uncertainty is one of the novel parts of this research that is really interesting. When you have forecast uncertainty, then it leads to more closures, as I mentioned. So a surge barrier manager will look ahead and they'll look at a storm surge forecast and they'll look at the high-end potential. There will be many times, the one thing they can't have is a case where they don't close the barrier when there is flooding. They can have cases where they close the barrier and it ends up not being as high of a water level, but they're more likely to err on the side of caution once they have a barrier. So if there's a small chance of exceeding the trigger threshold for flooding, then they'll close the barrier. And a good example of this shown with New York, with Stevens Flood Advisory System, with the link on the bottom right shown here, is this is just one case of the red of a forecast. So the red, it's about a 4-day forecast using Stevens system. The red dots are observations. The magenta line is the forecast water level over about 4 days into the future. And the gray area is the uncertainty, a 90% confidence interval. And you can see how the 95th percentile almost reaches 7 feet during this forecast. That's 3 days ahead or 2.5 days ahead of where the forecast was launched, where the red dots end, the present time on the vertical line. And really we'll be looking at 1-day forecasts. So it's maybe more uncertainty than you would have within 1 day. But it's a good example of how the water level in the forecast, the high-end potential water levels are higher than the central forecast. And here's what actually happened during that week. So the red dots again are the observations. So the peak water level itself is much lower than what the high-end forecast gave. So it's that additional increment that we want to account for that would influence and lead to more closures, because the high-end uncertainty often is significantly higher than the actual water levels. So we created a simple regression model. We accounted for the fact that the uncertainty is a function of storm surge. If there's a bad storm, then there's even larger uncertainty. And so we made this simple regression model, and we account for that difference between a 95th percentile in the forecast and the actual water level. So we add that increment onto the historic semidiurnal tidal maxima that we use. And that gives us a simple way of accounting for this uncertainty. In reality, we might, you could do something more complex where you have a randomness to it or something, but I'm not sure it would make any difference. And we'll probably want to go back and just evaluate that. Okay, and the last thing is the sea level rise projections. We also add those on, as I mentioned. Here's a distribution of sea level rise. For most of what I'm showing today, I think we're just used the 90th percentile and the 50th percentile and the 10th percentile. But this is the whole distribution. There was one analysis where we looked at this full distribution of sea level rise with a more complex analysis, but it's not what I'm presenting today. And so we're mostly focused on the RCP 4.5, which is a moderate emissions future pathway, which is closer to what we're on track for right now. But I'll briefly show the RCP 8.5, which is a high emissions pathway for human CO2 emissions. And as I mentioned, we just superimpose those on the water levels to estimate the trajectory of future sea level rise. We'll be using these sea level rise data every decade from 2020 to 2200, year 2200. All right, and so here's a first plot of results. This shows the closure frequency when we have moderate flood level as our trigger. So that's a lower flood level that's met about once per year today. As you can see at 2020, it's a frequency about once per year. And the diverging dashed lines are the 90% or the 80% confidence interval, actually, from the 10th percentile to the 90th percentile. So you see there's a lot of uncertainty in the closure frequency going forward. And another thing you see is that it's an exponential increase in closures. So this would lead to a lot of barrier closures, this trigger water level. So here's another case where, and this is actually what the Corps of Engineers is using as their trigger water level, 7 feet above mean sea level or NEBD 88 or 2.13 meters. And that leads to a lot lower number of closures, although rising exponentially still. And the uncertainty due to sea level rise is again very large. If we have more sea level rise, like a 90th percentile of the RCP 4.5, then that could lead to a very rapid rise in the frequency of closure, as shown by this upper black dashed line. So two main conclusions are the trigger water level choice has a strong influence on the number of closures, as shown in the right panel there, red versus blue. And then also the annual gate closure frequency has a high uncertainty due to sea level rise, the big spread between the dashed lines. And also another one I would say is that there's this exponentially increasing frequency of closure required if we have a constant trigger water level and we don't change that in the future. But then the Corps of Engineers actually in their study is proposing using a different management strategy, which we'll call management strategy number 2, where they set an annual maximum of closures on average that they would allow. And so 1 every 2 years is 0.5, a frequency of 0.5 per year. And that's, and they also propose potentially using once every 10 years. So that would be 0.1. In this presentation from here on, we'll sometimes be using this management strategy where we say, well, if law capped the number of closures at 0.5 per year or 2-year return period flood, then we get a whole different set of results. And you no longer have the exponentially increasing frequency of closure. You just have a 0.5 closures per year on average. And we'll show how those results affect the story of the future in one of the next few slides. So one other thing I had mentioned is the forecast uncertainty being important. So the red line, the black line here shows the case where you just use the historical water level maxima to represent the random variability of storm surges. The red line includes that forecast uncertainty, that simulated forecast uncertainty. So basically closing on the 95th percentile whenever that threatens to exceed the water level trigger. So important points here are the forecast uncertainty leads to more barrier closures. Future forecasts, I'll note that future forecasts will be better than today's forecast. So maybe this is overestimating that forecast uncertainty. If anything, our approach here, using our current forecasting system to create that model and the uncertainties that we've observed in the past year, if anything, it's conservative and it overestimates the number of closures. The reality is probably somewhere in between this red line and black line, because weather isn't, in the future, you will have better forecasts with lower uncertainty, but weather is an inherently chaotic process. And so it has some unpredictability, and there will always be some uncertainty in storm surge forecasts. All right, so now if we look at barrier closure management strategy number 2, where we're capping the closures at 0.5 per year frequency, a 2-year return period storm, these are the results, and mainly focus on the black, that's RCP 4.5 first. So RCP 4.5 with that 2 point, so basically you're going to have to, the key is that you'll have to raise your waterfront if you don't want to have flooding. You're not going to allow the frequency of closures to increase beyond 0.5 per year. So instead, you would have to raise your trigger water level. And so you'll have to, if you're going to protect everyone from flooding, you would also have to raise waterfronts for every location that has populated areas. So this is the water level trigger increase over time going into the future, or similarly, the waterfront elevation that you would need. So as I mentioned, we're looking at a 2.13 meter trigger water level for starters. So maybe you could start at that point. But then going forward, that trigger water level would have to be raised as soon as 2040 with a 90th percentile sea level rise case if we're unlucky, or with a central estimate of sea level rise for RCP 4.5, that's about 2060 or 2065. When that would no longer be sufficient, you'd either have more than 0.5 closures per year, or you're going to have to raise your trigger water level. And therefore either let people flood or raise waterfronts. So that's an important, that's a really sort of a quantification of the challenge of sea level rise with this study and with surge barriers. They don't address frequent flooding unless you're willing to allow them to be closed more frequently. All right, so on the right are some of the summaries of the main points. A higher water level trigger requires higher waterfront seawalls to stop flooding. This can lead to a longer system useful time horizon. If you raise the water level trigger, then for example, to 2.6 meters, then your system of surge barrier and raised seawalls can last to at least 2070, according to this point here. And that's with bad luck with sea level rise, but with central estimate of sea level rise, it could last through the early part of the next century. So it's a longer system useful time horizon, but it requires raising seawalls high. And this has a very large uncertainty. We're not showing the 10th percentile, we're only showing the 9th percentile sea level rise result and the central estimate, the 50th percentile sea level rise result. So there is a chance of having better luck and having the system last for a longer duration beyond what these lines show. The Corps of Engineers sea level rise trajectory is shown in red, and that, as I mentioned earlier, it's a 2 feet of sea level rise by the end of the century, and so it's more optimistic about the duration that the system would last. I will note it's not necessarily that that's wrong. Right now, the sea level rise trajectory is more similar to that than it is to the RCP 4.5 central estimate. But there is potential that there could be ice sheet collapses that would lead to a rapid sea level rise change in the future. So it's really, there's just this very large uncertainty in sea level rise. All right, so next result is the frequency duration analysis. And so results are shown here. So not only do we have the exceedance frequency, now that's shown on the, or as before it's shown on the y-axis, we also have the duration of consecutive semidiurnal tide cycles over which there's a closure. And so the present day case for a 1-day duration closure has about a 0.1 exceedance frequency. This is for the 2.13 meter threshold, close to major flood level. And as you go forward, and the frequency of a 3-day closure is about 0.002, so 1 in 50 years. So a very low frequency. But as you go forward with the 2050 median sea level rise estimate, you can see how the frequency increases and the duration increases because it moves toward the right along the x-axis and toward upward on the y-axis. And then by 2100, the median sea level rise estimate, you see it rises even more. So you have a case, for example, of a 4-day long closure being a 1 in 10 year event, a 0.1 exceedance frequency. And the one semidiurnal tide cycle duration frequency or closure case is about 3 times per year at that point. So that's becoming a high frequency event to have a closure needed of just 1 day. So if using a constant water level trigger, sea level rise causes increasing closure frequency and closure duration. That's an important conclusion. So here's the final conclusions of this chapter of our research. First, the trigger water level and forecast uncertainty both strongly influence the annual number of gate closures. If closures are managed by the constant water level trigger, strategy 1, then sea level rise causes an exponential increase in the gate closure frequency and a lengthening of the closure duration. The probability of trapped river water flooding, I hadn't shown this, but it is in the paper, is presently very low. Increasing sea levels also increase the probability of trapped water flooding behind the barrier from rainwater and river water, but the closure frequencies have to rise to a very high level, 10 or more per year, before that starts to become a problem. And you need more than 60 centimeters of sea level rise. And so that closure frequency problem is a much bigger challenge. The trapped water is very low probability until you start having a real high frequency of closures, which we've already noted is not supposed to be allowed. And then lastly, under strategy 2, if closures are managed by a maximum gate closure frequency instead, then you have to raise seawalls and you have a combined barrier seawall system if you want to have protection against this flooding. Or of course, retreat is another alternative than raising seawalls. And the useful time horizon for that system was defined. And this research can help inform the required seawall heights for the harbor and tributaries study and for their benefit cost analyses. So that's one utility of this research that we've been doing. All right, so next I'll speak, the final part of the presentation is on the effects, some new research that's still preliminary. It's the next chapter of Ziyu's dissertation on barrier closure effects on the estuary physical conditions. So this research is being done with the Stevens Estuary and Coastal Ocean Model and on the NIHOPS domain, both of which were developed by Nikitas Georgis and Alan Blumberg. These are highly validated models against salinity and temperature observations, but I'm not going to present that here. But that system runs real time, all the time, NIHOPS, and also provides, within its flood advisory system, it provides flood forecasts. So what we'll look at here are the 3 barrier system that includes Verrazano, Arthur Kill on the bottom left, and Throgs Neck on the top right. We're modifying the model bathymetry essentially in the model to represent fixed surge barrier components, and that's the red dots now with a zoom in shown on this map. So those are the fixed components off to the sides in this sort of simplified, very coarsely resolved surge barrier. And then the white dots are the open and closed barrier gates that can be open and closed, thanks to HDR Incorporated, who provided code from their version of this same model, CCOM, that we've embedded into our code to have this capability for doing that during a model simulation, which was not normally the case, that you could change the bathymetry during a model simulation. And then lastly, the forcing for tide and storm simulations is one. First, and today I'll just be showing tide simulations, but there will eventually be storm simulations also. I think we can get all our main conclusions out with just the tide simulations where there's no storm. We look at 1, 3, and 5 day closures. We looked at closure frequency of 1 monthly, but also yearly, once per year. And lastly, we look at low stream flow, about 150 cubic meters per second from past Albany, and then also mean stream flows, about 500 cubic meters per second past Albany. All right, so one example of this type of results here is shown on the left. So it's the salinity stratification. It's the bottom salinity minus the surface salinity. The y-axis is the up estuary distance along the central channel of the Hudson from Battery at 0 northward. Poughkeepsie's at about 120. And then on the x-axis is the time of our simulation in days. So, and we're keeping all the complexity of real tides in these simulations because they capture the fact that every month there's a higher spring tide and a lesser spring tide. And we're going to focus on those spring tides, sort of looking at the management scenario number 1 that we mentioned before, where the system is being closed more frequently, maybe once per month, at some point in the future due to a lot of sea level rise. So the white line is the salt intrusion limit, defined as 1 part per thousand salinity. And the red line is the water level with an arbitrary scale. So you can see those neap tides where it's got a smaller excursion and the spring tides with a larger excursion. So that's the control simulation of salt stratification with neap and spring tides driving respectively the salt intrusion up estuary and then down estuary. And here's the case with a 3-day closure with mean stream flows in both these cases. So on the left is the altered result from the control. On the right is the difference between control and the simulation, the change in stratification in terms of a percentage. So you see there's a real strong, there's a salt intrusion slides up estuary an extra 10 kilometers or so. And there's very sharp stratification, and then it goes away and returns back to normal. If we look at the case of mean stream flow in 3 separate 3-day long closures, and so these are all happening on the biggest spring tides, maybe even a king tide in one or 2 of those cases, so we're not really looking at storm driven cases yet. That's some future work we have to do. But, and so you see that every time there's basically a recovery in the case of mean stream flow, or it's borderline recovery back to normal before the next monthly closure occurs. And here's a cross section of what one sees off Manhattan of the stratification, salinity stratification. It becomes very strong when you have this closure, about a 25 part per thousand stratification from top to bottom, which never typically exists in the Hudson. So you're just getting this very, very strong stratification. You turn off the tide mixing completely. So it's like neap tide, or it's dramatically more extreme than what occurs normally on neap tides. And so you strongly stratify the system. You have that water it has higher density, and it wants to slide up estuary and flatten out. So you have a salt intrusion that slides up estuary without any tides stirring it up and mixing it and preventing it from sliding up the estuary. So that's why you get this salt intrusion penetrating. In this case, it's shown as going about 30 kilometers up estuary during each closure. And then here's a case with low stream flow. So we haven't done as many simulations with low stream flow. We still have a few more to do, but this is a case of 3-day closures with low stream flow. So the low stream flow case has weaker or a slower recovery back to normal conditions, and it really doesn't occur within the 1-month period. And so we're still trying to quantify exactly how long it takes for complete recovery, but it's longer than a month. So it's months for recovery. And you also see that, therefore, the salt intrusion pushes further and further up estuary with each successive closure. And it is getting past Poughkeepsie at 120 kilometers, which normally doesn't happen except in drought. And so that is one concern, obvious concern with using this barrier too much. So again, this is really looking at the sort of scenario barrier management strategy number 1, which the Corps isn't recommending be used. But it is something that we do need to evaluate and consider, because once these systems are built, it is possible that they'll be misused. All right, so next slide. Now just some tables. I'll be brief here and maybe skip through this pretty quickly. Basically, we're looking quantitatively at the duration it takes to get back to normal, trying to quantify the spatially average salt stratification in the entire estuary. The black lines are the control, and the other different colored lines are different durations of closure. So we're looking at this more quantitatively, trying to quantify the time period for recovery, et cetera. And so another slide showing the 3-day closures on the left, salt intrusion length, and how, so the deep red color, or the control case is shown in green. And you see that the case with a 3-day closure takes several weeks for recovery. This is a case of mean stream flow. So again, as I mentioned before, with dry stream flow case, then it takes even longer for recovery. And then on the right, it's a 5-day closure. So the difference between 3-day closure and 5-day closure is fairly stark. With a 5-day closure, you have a 40 to 60 kilometer salt intrusion increase during the closure. So the duration of closure and the stream flow, be it dry or average, both have a really strong impact on the duration it takes, or the period, the duration of time for recovery. And again, I'm actually going to skip this because I want to leave more time for questions, but we're just quantifying this numerically and looking at these time periods for recovery. And I'll recap that a little bit also in the conclusions in a moment. So preliminary conclusions: closed barriers cause very large estuary physical changes. The spatially average salt stratification increases up to a factor of 4, and the salt intrusion length by up to 60 kilometers, as shown in that last case of 5-day long closures in mean stream flow. It's actually less, the increase in salt intrusion length is less during dry stream flow because you already have a long salt intrusion length during dry stream flow. The recovery time to normal conditions depends on the closure duration and the stream flow. Cases of low stream flow can have changes that require multiple months for recovery. I think an overall conclusion is that monthly closures don't generally provide, under all conditions, enough recovery time back to normal conditions. And so that salt can keep migrating up estuary if you're closing the system every month. But annual closures or less frequent, such as what the Corps was proposing, once every 2 years or once every 10 years, provide ample time for recovery. And lastly, one thing we're not looking at here is what the impacts on oxygen or ecosystems would be explicitly. We're just looking at the physical changes. So in order to understand if these stratification increases would be a problem, one would want to do biogeochemical simulations, water quality simulations to understand those oxygen impacts. Okay, and some future work is that we need to finish the low stream flow barrier closure simulations for 1-day duration and 5-day durations, which we didn't do. We'll put the recovery times from closures in context of estuary dynamics literature. That was a suggestion by Dave Ralston, which the ZIU is working on now. He's looking at some work by McCready, and it's basically several different studies looking at how we could compare our results to theoretical estimates of how long it takes for recovery of the system after these closures. We're going to simulate nor'easter conditions and tropical cyclone conditions. We expect that with the very high stream flow cases that'll lead to really strong stratification, which we're already seeing, but probably a quicker recovery if you have high stream flow. As we saw, a higher stream flow leads to faster recovery time. We'll compare our modeling to the Corps of Engineers modeling of estuary stratification results for open and closed barriers. I think that'll be important to just have a better understanding of how our results compare. Their modeling is more detailed and explicitly resolves the gates. And ZIU will be writing a second paper and dissertation chapter on the physical estuary effects of closed barriers. And lastly, we have additional research proposed to look at the effects of surge barriers and climate change on tidal marshes in the Hudson and also on ecosystems, with a similar strategy to this past project where we have some research and some workshops that bring people together to talk about a wider range of topics. And that would start if funded later on this year. And one last note is that this has been a really rewarding study, and we want to thank everyone for being a part of it. Basically was a new model of academic science involvement in a federal study, which I feel is obviously I think is much better than having academic scientists, leaving their expertise and their local knowledge to public comment as giving inputs. So it's a really good opportunity. We have helped the public and the government stakeholders understand the harbor and tributary study and these possible impacts. We feel we've improved the HAT study science. And we're also creating and sharing methods and tools along with our publications that can be used at other locations, such as the New Jersey Back Bays study, where they're also looking at storm surge barriers. All right, so that's it. Thank you very much for everyone joining us. I look forward to hearing some great questions.
Great, thanks Philip very much. You can hear me, right?
Yep.
Okay, good. So just want to invite people again to either post questions in the Q&A. If you put your cursor again down to either the bottom of the Zoom screen or the top of the Zoom screen, you will see that, or as well raise a virtual hand. There's one question from Vanessa Dornish. What is your process for sharing results with the Army Corps?
Basically, all of our results are being posted on the website. The Corps of Engineers has been part of this process as one of 2 of the people on our 14-member advisory committee. And so they have some role in guiding the project. And in our workshops, we're sharing results and interacting with them, showing them results, like basically preliminary results. So they're getting a good look at any of the results that we have.
Great. Again, let me invite other folks to jump in either with a question or a comment in the Q&A or by raising a virtual hand. I am looking at the participants list and not seeing any hands. There's one. Dave Ralston, let me invite you in there. Dave, your line should be open.
Can you hear me now?
Perfectly.
Great, thanks. Yeah, so Philip, on one of your previous studies with Stefan Talka, you looked at the time series of storm tide frequency from the battery and noted there was an increasing trend in storm tide magnitude, independent of sea level rise. And I guess I wonder, do you think that would be, how big a factor do you think that would be in your results for the first part of your presentation?
Yeah, good question. So is climate change impacting storms and making storm surges worse? And is that, are we making too much of a simplification to look at the past storm tides and assume that's the present day and future storm tide risk? And that we can just separately add on sea level rise. Yeah, so the present research for this region has shown tropical cyclone induced storm surges are increasing a small amount. Reza Marsuli at Stevens actually did this work with Ning Lin and Kerry Emanuel and others. But it's about 10% of the increase due to sea level rise. So it's something which we could include, but I think there's a high uncertainty around those results created using climate models and Kerry Emanuel's tropical cyclone model. So that, because sea level rise is 10 times larger factor, we feel as though it's a reasonable assumption. But that is a possibility that storm surges from tropical cyclones will get larger. And then extratropical cyclones, nor'easters, et cetera, have been quantified in climate models by Brian Colley at Stony Brook, and they basically found a lot of uncertainty in the future, and any future change in storm surges from extratropical cyclones, and there wasn't any clear trend in the future from that. So that's our reasoning. In terms of the past work showing that there's an increase in storm tides at New York Harbor, it may not be that the storms are getting worse, it may be, or that the storm surges are getting worse. It may be caused by landfill, dredging, and other changes around the region. And we're still studying, trying to understand better what did cause that. So that's still to be determined what the actual causes are. But if it was caused by dredging and landfill, then that's probably less of a concern for the work we're doing here.
Thanks, Philip. A question from Roger Wang saying, is it possible to half open the gates so that the stratification issue would be less, but still afford some protection? The
idea of, it's a good question and something that we wonder if we're oversimplifying. With the case of stratification, I don't think you can half open the gates to allow salt intrusion in. You'd be opening them on flood tides, and so you'd be allowing, there may be some clever approach for opening them part-time, but I think you can't solve the salt intrusion problem, which is a slowly developing, the salt intrusion is the salt within the estuary collapsing. I guess you could pulse the gates open to try to mix it up by having the tides come in every once in a while, but it seems pretty complicated to do that. It has come up more when it comes to the trapped water flooding behind the barrier from stream flow and from rainfall. If that water is rising and becoming a threat, then they could potentially pulse open the auxiliary flow gates, and that's one thing that's been proposed, and they can let water out every time there's a low tide offshore. So it is something that there is more complexity to these barriers, and there's also the 2 or 3 barrier systems that are used, and so there's more complexity than one we're looking at. But I think what we do here is we illustrate the general processes and the general considerations.
Great. A couple more questions here in the Q&A from Darlene Finch. What do you hope the Army Corps will do with the results of your work? And do you think it might alter their analysis?
I'm hopeful that we've already altered the Corps of Engineers analysis a bit over the past few years, starting from the 2018 study. Yeah, so I hope, I think that we've run workshops and we brought a lot of people together, and the Corps of Engineers attended them always, and in some cases with several people. And then also this research, in both cases, I think we're having some influence. The Corps of Engineers has been a big part of the process and been observing and playing a role in the research all along. So I think that we're definitely having some influence, but it's hard to gauge.
Yeah, I'll just add, I think it was a really constructive dialogue with a really good mix of folks there, and the Army Corps in the conversation, part of the conversation, very actively engaged at every step of the way. I don't know if there's anyone in the Corps on who would like to jump in on that question from your perspective. I'd certainly invite you to, and if you do, just raise a hand. In the meantime, I'll jump to the next question from Adam Paris. You mentioned that weather forecasts will get better. Does that factor in potential variability in storms resulting from climate change?
I think even if storms are getting more intense, that'll be something that's captured in a weather forecast on the short time scales. You'll see the storm as it is, at forecast time, and launch a forecast for the next few days. So I think that will be part of, the models will be capturing that in forecast mode. There won't be something that fundamentally becomes unpredictable about storms. They'll have more moisture, and that's a major driver, or more heat, more, warmer sea surface temperatures that drives them. But I think it'll be captured in the forecasting. So I still think that that's basically, we'll see improved forecasting, but it's hard to know how much, and it's hard to predict. So in this work, we basically were conservative about that forecast uncertainty, and we use today's forecast uncertainty to look at future closure frequency.
Great. And another question from Roger Wang, which is, how might the inundation pattern differ with the gates in operation or versus a no gate situation?
Well, the inundation pattern with the gates closed, maybe he's getting at the question of, obviously with them closed, the inundation within the barrier system will be reduced, if not completely, potentially completely eliminated. But offshore of the barriers, you'll have the inundation, and there is some potential for having increased inundation offshore of the barriers. For the gateway system, that's been quantified, and because you're near the open ocean, that excess water basically has the opportunity to radiate into an infinitely large space. So you have a small increase in water levels and maybe a small increase in flooding, but not a large one. Whereas if you're inside the estuary and more of an area, that's enclosed, such as along the Hudson River, and you have, if you have a barrier system, say if you think about the Verrazano Narrows barrier or the Throgs Neck barrier, then you're inside the system and you have a little more of a problem with that water that's kept offshore being inside that system. And so it becomes more of a problem. For a 100-year return period flood or storm tide, the water levels can increase by 10 centimeters, 20 centimeters, a small percentage, maybe 5% offshore of that barrier, and that can lead to more flooding. And so the Corps of Engineers is accounting for that in their work, and they're looking at how they'll have to have higher seawalls outside of the barrier system. And that's a major, and that's something that's being added into their benefit cost analysis. I think with the Throgs Neck barrier on Long Island, that's the case where that became the biggest issue, and where they would have to account for those extra costs of raising seawalls outside the barrier system to prevent that additional flooding.
Great, thanks, Philip. Roger, if that hit the mark, great. If it didn't, you can throw something in the chat and we can bring you on. At this point, I don't see any raised hands or any additional questions in the Q&A. We do have time for probably maybe one more question or two if someone's got something they want to hear from Philip on. Let's give it 10 seconds here. But
no rush. We could
throw
give
something in the Q&A or raise a hand. Here we go. Question is, given all sea level rise projections, won't there one day be sandy level flooding on every high tide twice a day?
Yeah, that's the challenge of sea level rise. If, that could be, that may be 200 years away. Sandy was a water level about 11 feet above mean sea level. So that would be about an 8-foot storm surge on a 3-foot tide. So you'd need something like 8 feet of sea level rise. So that, you know, in worst case, sort of 99th percentile sea level rise estimates, that's potentially going to happen at the year 2100, maybe even lower than 1% chance, or 99th, higher than a 99th percentile. So, but that will, if, you know, the amount of sea level rise already baked in, as some say, is several feet. And so there's a chance we will eventually have that much sea level rise. It might be 300 years. It could be, you know, further out, really far out from 2100. In that case, you know, that's the thing. The surge barrier is a storm surge protection. It's not a sea level rise solution. It can help with sea level rise temporarily, but it's not a sea level rise solution. And I think that's one of the things that is a challenge to deal with here. If we have low end sea level rise of 2 feet this century, it's much more manageable. If we have 8 feet of sea level rise, then then you know, that's a dramatic, maybe insurmountable problem.
Okay. All right. At this point, I don't see any other hands raised or any questions in the Q&A. And since we are just about 2 minutes or so from top of the hour, I think we should just, oh wait, there's a last quick question. Is that Tim McInerney? Your line is open if you want to jump in. Are you there? Is your line open? Okay, here he put in the chat. Prior work associated a reduction in tidal range behind surge barriers, if I understood correctly. This would indicate the highest tides would not be as high as they would be otherwise. Does closure frequency analysis take into account this passive reduction in tide elevations? And Philip, you've got about 1.5 minutes for an answer on this one.
Yeah, that's a great question. And that's one thing we're not accounting for. We are assuming that the water level when the gates are open remains the same. So we did find that there was a 3 to 6% reduction in tide range behind the barriers when they're open. And so that is another factor that will slightly reduce the high tide levels and the chance of flooding on spring tides. And that reduction is actually bigger for spring tides and even bigger for king tides. So it might be a 10%, you know, maybe 10 centimeter reduction in the peaks of those high tides. So that was not incorporated in this analysis. So good question. And that's just one more dimension of complexity that could be put into it.
Great. Okay, so we are at time. Just a couple of reminders to folks as you look at the slide up on the screen. The project page in the middle, http://philiporton.com. Please feel free to go there for reports and more information. This presentation and recording will be made available there. So if you want to watch it again, or there's something you wanted to better understand, you can go back and look at it, share it with others, encourage you to do that as well. If you're interested in receiving the report that will be coming out in the Journal of Marine Science and Engineering, you can email Philip and he will provide that to you as well. Philip, anything you want to add? And I see Chris Schubert saying thank you, and there was an earlier comment saying great presentation. Philip, over to you.
Great job, Bennett. Thanks a lot. Thank you, everybody.
Okay, thanks everybody. Have a good rest of the day.
Good job, Ziyu.